All right, you might remember when we started this course, I was talking about how this was a generalization of the kinds of functions that we encountered in Calc 1 and Calc 2 that take a single number as an input and produce a single number as an output. Like y equals x squared, you plug in 2, you get out 4. You plug in 5, you get out 25. We're now the whole point of Calc 3 really is to take calculus and lift it up to other kinds of functions that maybe take in 5 inputs and spit out 3 outputs, excuse me. So the first of these examples, formally anyway, that we're going to encounter here are vector-valued functions. In section 3.1, and indeed the whole chapter 3, concerns itself with vector-valued functions. That's somewhat of a vague term. These vector-valued functions really could represent any kind of function that spits out a vector, a string of numbers. But in this particular chapter, we're talking specifically about functions that take in a single number and produce a string of numbers like a vector. In that case, mathematically, we would be talking about functions r of t that map the real numbers, in this case, to three-dimensional space. An example of that, an example of a function that takes in a single real number in vector notation might be something like t, 2, and t squared. And if I look at, for example, r of 0, the way that I calculate that is just plug in 0 everywhere I see a t, and what I get is 0, 2, 2, 0. And it's not super important that we focus on this particular function. The point is that it takes in a single number t, and it produces a string of numbers, a vector, in this case a three-dimensional vector. We also think about two-dimensional vectors, and we think about 20-dimensional vectors. So the big goal of this particular section is just to understand vector-valued functions in the context of a single input and 3 outputs. This is most useful when you're imagining something traveling through space, for example, a bird flying through the sky. At each moment in time, that bird occupies a different position, and so it might sort of sail across the sky like this, and it might see a tasty insect and sort of divert itself, and then continue on its way after it catches the insect. So, yum yum, right? Caught I don't know, some kind of moth or something. All right. And the other thing, so we're pretty low key in this section. The other thing is just to be able to compute limits of vector valued functions, and I'll give it away right here at the front. The limit of a vector valued function is just the limit of each of its component functions. All right, what's the big idea here, or the narrative? A vector valued function, of course, is going to produce a vector sort of in standard position. So if we put the origin down here, then what we're really seeing is a collection of vectors that depend on different times. So the tip traces out the location. It traces the path of the bird as it's flying through the sky at each moment in time. So I plug in T1 and maybe I get this position, T2, T3. Different times give me different positions. In fact, this is called a position vector in much of this chapter, and the prevailing metaphor is something traveling through three-dimensional space as a function of time. Where is it at t equals 1 second? Where is it at t equals 20 seconds? And so on. All right, the notation for vector-valued functions is really just vector notation with an independent variable thrown in, like t. So you'll see that over and over again in this chapter. In fact, let me go to the book here, and you can see that. Should have brought the book up before I started this recording, but all right. So let's go grab the book. interweb is slow today. It's a nice sunny Saturday afternoon. I suppose all the hamsters that push the bits around the internet are taking the day off. All right, so we're in Chapter 3 now, Vector Valued Functions, and we're talking about the introductory section. The notation's relatively straightforward. In 2 dimensions, you just have an ordinary function f of t times I plus another ordinary function g of t times j. In 3 dimensions, there's a k component, and we'll typically call that h. We might also write it in this vector form, f of t comma g of t. So that's pretty much that. There are a few vector valued functions that I want you to be able to kind of identify. One of them is something, for example, involving sines and cosines. If you see cosine t, sine t, you should immediately start thinking circles and ellipses. If the coefficients are the same, it's a circle. If the coefficients are different, it's an ellipse. So, for example, in A here, that's an ellipse. All right. Of course, this works in 2D, works in 3D. It's very closely related to the stuff you learned about parametric curves in section 1.1. It's just that the context is a little different. Instead of solely focusing on 2 dimensions like we did in section 1.1, we're now lifting ourselves up to 3 dimensions, but that's really nothing more than adding another component to the vector valued function. Sines and cosines lead to circular paths, linear functions lead to linear paths, and collectively these traces through space are called space curves, and the curve is traced out by the tip of a vector. Let's, for the sake of time, just jump straight to some of the exercises. Let's look at problem 6 from the end of the section. So given this vector valued function, let's find the following values. This is a 2-dimensional vector valued function, so f of t is just the function t, g of t is the function t squared plus 1. First question is, what's the limit as t goes to -3? Well, if you look at these 2 component functions, they're both continuous. So taking the limit is the same as just plugging in the value t equals 3. So because they're continuous, CTS is my abbreviation for continuous, the limit as t goes to -3, r of t is just r of -3. That is, after all, the definition of continuity, that the limit equals the value of the function at the point. And r of -3 we just obtained by plugging in t equals -3 everywhere. So in the first slot, t equals -3, and in the second slot we get -3 squared plus 1, that's 10. So the limit as t goes to -3 of this function is just -3, 10. Great. Normally we don't take limits of continuous functions like this. Normally we're interested in limits of functions that are problematic. And the kinds of problematic functions that we should be preparing ourselves for are difference quotients, where you can't just plug in the limiting value when you're doing the derivative. And we're heading to that very quickly. So that's why we're talking about limits here, even though in this toy example we're not really seeing that. Of course, r of -3, we just computed it, is the vector. This is, after all, a vector valued function. It's the vector -3, 10. Part C, is r of t continuous at x equals -3? Yes, because the limit up here is equal to the value of the function here. So yes, because the limit equals the value of the function. A terrible abuse of notation here. I should never be writing stuff like that, but you know, I'll expect better from you in your homework. And what about r of t plus 2 minus r of t? Well, let's plug in r of t plus 2. I better get myself some more space here. R of t plus 2. Everywhere I see a t, I'm going to replace it with t plus 2. And in the second slot, that's a little complicated because it's t squared plus 1. So I take t plus 2, quantity squared plus 1, might be a good idea to expand that out. T plus 2, t squared plus 4t plus, 4 plus another 1, that's 5. Great, that's r of t plus 2. Let's do r of t. Well, we already know r of t. It's simply the function. And let's subtract r of t plus 2 minus r of t. When we subtract, what's going to happen? Well, we're going to get a little bit of cancellation in the first slot there. So what's left behind is 2. In the second slot, a little bit more cancellation here, and this turns into a 4. And so in the second slot, we get 4t plus 4. And so that's the difference. This is a little bit of a precursor. You could imagine that this might be a kind of difference quotient here. If you divide it by 2, it would be sort of the difference quotient for h equals 2. We'll talk more about that in the next section. Let's talk about 14. Describe the curve defined by this vector-valued function. If you look at this thing, you see that everything in sight is linear. So this is a line of some sort. Can we figure out what kind of line it is? Sure we can. If you go back to the section on lines and planes, you know that what you can do is separate this out into a constant vector plus t times another constant vector. And doing so, we get the vector 1, 2, and negative 1. And we get the vector plus t times the quantity or times the vector. In the first slot, we get a 1. In the j slot, we get a 5. And in the k slot, we get a 6. So that's the vector form of the line. We can see the parameter t here. This just describes a line that goes through the point P, say 1, 2, negative 1, and goes in the direction, maybe goes in the direction, oh gosh, draw a line, Albert, like this. It's going to go in the direction of the vector 1, 5, 6. So the line through P in the direction 1, 5, 6. So there's a nice description of this vector-valued function. Let's talk about 16. So the domain of a vector-valued function is really just the largest possible number of t-values that you can plug in. And you usually want to write this as a collection of sets. It's going to be the intersection of the maximal domains of each of the 3 components. So in the first component, we can use any real number as the domain, any real number. In the second component, we know that t minus 3 has to be greater than or equal to 0. Put another way, t has to be greater than 3, greater than or equal to 3. And in the third, we have to avoid what? We have to avoid the denominator being 0. When is the denominator 0 here? Well, set 2t plus 1 equal to 0 and solve for t, and you get negative 1/2. All right, if you put that on a number line, this is the real numbers. Here's 3, so we're okay if we stay bigger than or equal to 3. And then we have to also avoid t equals negative 1/2, which is down here. But that was already excluded, right? That's excluded by the condition t greater than or equal to 3. So the domain is just t greater than or equal to 3. That's the largest possible collection of t-values for which this function is well defined. All right, in 23 and 26, you're asked to eliminate the parameter t and write the equation in Cartesian coordinates. Then sketch the graphs of the vector-valued functions. All right, this is really the process is essentially acknowledging that this is the x-coordinate in Cartesian coordinates, and this is the y-coordinate in Cartesian coordinates. So for number 23, we have x equals t cubed, and y equals 2t. X equals t cubed, and y equals 2t. I'm not a huge fan of solving for t in the x equation. I do like my chances for solving for t in the y equation. So I'm going to be lazy and do that. T is equal to y over 2. And then I'm going to substitute that into here. X equals t cubed over 8. Sorry, y cubed over 8. And that's a Cartesian equation. Normally we would have y as a function of x, but just because of the way things worked out, we have x as a function of y. But you know, we're all in Calc 3 now. We should be comfortable with that. Here's the x-axis, the y-axis. We expect this to be a cubic, but now the cubic is kind of sideways. So that's x equals y cubed over 8. So this vector-valued function up here in number 23 is tracing out sort of a sideways cubic. Let's look at 26. Same question, a little bit different. It's trigonometric instead of polynomials. Let's try the same trick. So for number 26, we have x is equal to 3 sine t, and y is equal to 3 cosine t. Now remember, I'm trying to write the equation, some equation that describes this space curve. I'm going to use what I know about sines and cosines to play a bit of a trick, and I'm going to square both of these. X squared equals 9 sine squared t, and y squared equals 9 cosine squared t. Why am I doing this? Well, if I add the two equations together, x squared plus y squared equals 9 times sine squared t plus cosine squared t, and then use the Pythagorean trig identity, I get that x squared plus y squared equals 9. That's a Cartesian equation. I've eliminated the t variable. Eliminated t and expressed solely in x and y. And we recognize this as a circle of radius 3, center, origin. Honestly, if you see a vector-valued function like this or like this, I want you to be able to recognize that that space curve is in fact a circle of radius 3 centered at the origin without going through this conversion to Cartesian coordinates. But if you need convincing, this is the way to go. In 28, we want to use a graphing utility to sketch each of these. You know, I'm not entirely excited about my choice here. It's just some sort of random collection of variables. This is extremely difficult to visualize, and I'm going to jump over to GeoGebra, and we'll have a look at what this particular space curve looks like, and really just as a way of introducing you to this feature of GeoGebra. GeoGebra is able to plot space curves. Let's go to the graphing calculator. Remember, the graphing calculator is the 2D context, and this is a two-dimensional curve. And there's also the 3D context. If we had 3 component functions, then we would be using the 3D graphic calculator. In both cases, we have a function called curve, and it sort of prompts you with the kind of syntax that it wants. It wants an expression for the first coordinate, one for the second coordinate, tell me what the parameter value is, t in this case. Tell me where you want the parameter to start and where you want it to end. So I'm going to start with this sort of strange function. It's the exponential of cosine 3t. The exponential of what? Minus sine of t. I think I'm being really careful with my parentheses here. Okay, I think that's good. So that's the x-coordinate and the y-coordinate function, t. And then where do I want it to start? Well, I see sines and cosines. And just for the heck of it, I'm going to start with t equals 0, and let's go out to 2 pi, like that. Maybe I could have gone out to pi. 2 pi I chose because that's going to cover one complete period of the sine function. And it's going to do several periods of cosine 3t because cosine 3t is oscillating more quickly due to the 3. But I know that together they're both going to complete a whole period, and so that should trace out a closed path, which is what we see here. If I only go, say, half of 2 pi, let me go out a little bit here. Let's see if that changes things. Yeah, notice if I only go half of the period of the sine function, then I only see part of the full curve. So that's just intuition for me. I'm just kind of guessing. Because the sine function is there and this is periodic, I'm going to go 0 to 2 pi and see what I get. If I go more than 0 to 2 pi, it's probably just going to trace the curve over and over and over again. If you want to see how this is actually behaving, you can actually add a point that's controlled by a slider. So let me specify just a particular value. So you can always just create a variable and give it a value, say s equals 0, and hit enter, and that will create a slider in GeoGebra, and you can change the value of s. And then you can create a point that depends on that value. I'm going to do the same point, cosine 3t, sorry, not 3t, 3s, and then the exponential of minus sine t, like that. Oh, not t again, so used to doing t. S, like that. And that's now a fixed point called A. What's fun about this is if I slide this back and forth, I kind of see how the point moves depending on the value of the parameter. So you can kind of see, for example, for increasing parameter value, we're moving along the curve in that direction. And I can hit play, and GeoGebra will nicely kind of let it sweep through. And so here's, I don't know, it's a bird flying through the sky, chasing a bug, something like that. It's a space curve. It's a way of tracking some kind of object that's moving in the plane or in three-dimensional space as a function of time. It's incredibly useful in physics, engineering, all kinds of applications. Great. Let's go back and continue here. In problem 37, we're going to do a three-dimensional curve this time. So we're going to use GeoGebra and do a three-dimensional space curve, cosine t, sine t, and then this 0.3 sine 2t. Now, before we go to the technology, I want you to develop the skill of looking at a space curve and seeing if you can sort of infer some facts about the space curve without actually resorting to the technology. So when I look at this space curve, I see in the x component and the y component, I see my friendly cosine t sine t. So I expect something circular to be happening in this part of the space curve. In other words, if I look down from above on this space curve, I'm not going to see any of the motion in the z direction. All I'm going to see is circular motion. So when I plot this thing in GeoGebra, I'm going to orient the axes and look straight down from above. And when we do that, we should see a circle centered at the origin of radius 1. So now you might ask yourself, okay, so this thing's moving around in a circle in the plane, but it also has this k component, which is causing it to move up and down. It's causing it to oscillate in z. So what we're going to expect from this particular space curve is circular motion with the additional up and down motion of this z component, this sinusoidal z component. And you're going to get something like what they're calling a roller coaster. I tend to think of it as like a merry-go-round. You've seen merry-go-rounds. You get on the horse is going up and down, but then the merry-go-round is going in circular motion. I like to think of this as sort of the merry-go-round curve. But enough talk. Let's see what GeoGebra has to show us about this three-dimensional curve. So remember, GeoGebra has a 3D context and a 2D context. The 3D context is here in the 3D calculator. Fortunately for us, the syntax is very similar. It's just going to require an x-coordinate, y-coordinate, and a z-coordinate now instead of just x and y. So we start with the word curve, and we get a prompt now. And now we have another option. We have an option to enter three expressions, one for x, y, and z, and then the parameter and the start value and the end value. So I'm going to enter three parameters. The x-coordinate, of course, is cosine of t. The y-coordinate is sine of t. And the k-coordinate, let's go look at it, is 0.3 sine 2t. So 0.3 sine 2t, like that. All right, we've got the x-coordinate, the y-coordinate, the z-coordinate. Now we have to tell it, what's the parameter name? It's t. Where are we going to start? Where are we going to end? Well, where do you think we should start and end? I see a cosine and a sine t here. Maybe 0 to 2 pi would be a good choice. So let's try starting at 0 and going out to 2 pi, like that. And that looks good. And what do you see? You see this curve that sort of goes up and down, above and below the xy plane, like this. And as I promised, if we look at it from above, it's going to resolve into a circle of radius 1. See that? Circle of radius 1. What if I wanted this to be a larger circle? What if I want it to be a circle of radius 2? How would I adjust this? Let's go back to the curve and put the cursor in front of cosine. What are we going to do? Let's say we want to make it a circle of radius 3. We'll put a 3 in there. Hey, look. Intermediately, before I do the other 3, I got a 3 here and a 1 here. Notice now I'm getting an ellipse, and I still have this oscillation in the z direction, so I'm getting an ellipse that sort of dives up and down below the z, below the xy plane. Let me throw the other 3 in there. Okay, now we've gone back to a circle, and notice that circle has radius 3. We could also make the up and down motion more dramatic. How do you think we might do that? Okay, the amplitude in the z direction. Let's change it to, I don't know, 2. Changing it to 2, we see a much more dramatic swing up and down above and below the xy plane. And then the last thing I want to talk about is we see essentially 2 oscillations, 2 trips above, 2 trips below the z-axis. What if we threw like, I don't know, a 6 in there? Well, now we see 6 trips above and 6 trips below, right? This might be much closer to what you would experience in a merry-go-round, I don't know, or a roller coaster. Maybe more fun, or maybe not, depending on your fun with those kinds of things. I would probably enjoy it. All right, so that's not only is it useful to learn how to plot these things in GeoGebra, but it's also super important that you stare at these things and you sort of think intuitively about how these things are operating in particular planes and noting circular motion, linear motion, etc. So that's it for the exercise. This is a pretty quick section. I want you to look over all of the exercises at the end of the section, including the ones that I've touched base with today. And when you feel comfortable with the material, go ahead and head over to WebWork and do the assessment for Section 1, Chapter 3. Thanks a lot.